Okay, so those who have joined for the first time, please note that attendance is compulsory. If your attendance is 75% and more, then you get 10 marks, otherwise you get 0. So that is the only point you have to put down. So those who have missed some attendance because of back drop, I don't care. That is included the remaining 25%. Don't come to me later that I got admitted late, so give me 2 attendance. Please. There is nothing free. Only 25% is free. You can do the way you want. Okay? Alright. So in the last class we started looking at why process control is required. We said that the process control is primarily required for the 3 reasons. In the last class, what we have discussed is the process control is usually called for 3 reasons. The first reason is to suppress the effect of disturbances on the system. The second reason is to make inherently unstable process stable. And the third requirement is to optimize the performance of the block. So these are the 3 reasons for which typically the process control is called out. Okay. These are listed here. After that, what we have started looking at is for a simple system, what is the feedback control system, what is the forward control system, isn't it? That is what we have seen, isn't it? This is a typical example which we have seen earlier, where we are interested in maintaining the height of the liquid in the tank, and also we are interested in maintaining the temperature of the liquid in the tank. The disturbances in this case are Fi and Ti. Chemical processes are dynamic in nature, so disturbances will keep on coming, and whenever there is a input of the disturbance variable, these disturbance variables are going to measure your system, and because of that, some of your constraints and objectives may get violated, and that is the reason why you require control. So you need to monitor control variables continuously, isn't it? And whenever the control variables are going beyond their designated value. In such cases, you have to put external intervention in the form of control, isn't it? This is what we have discussed in the last class. So these are the examples of feedback and feed-forward system which we have looked at in the last class. In the feed-forward, we are saying that, let's say if you are interested in maintaining the temperature here inside the tank, what we are going to do is we are going to measure the temperature by using a temperature measuring device like thermocouple. And this measured temperature will be compared with the set point temperature, and the difference between Ts and Tm, that will give you the error, and that is the reason why the plus sign is given here and minus sign is given here. So these signs are very important. Later on you will see that based on the signs many things get changed. Okay. So in this case, what this minus sign and this plus sign is signifying, we are calculating here Ts minus Tm. Okay. So Ts minus Tm gives you error, and that error is given to the controller, and depending on the error value, the controller is going to modulate the steam flow rate to the tank so that the temperature inside the tank can be changed. Correct? So this is a typical example of feedback control system. Why we are saying feedback? Because whenever there is a change in Ti, that change in Ti is first impacting the system here, isn't it? So effect of change in the disturbance is first felt on the system, and then you are applying the control action. So that is why this system is referred as feedback system. The another system which we have studied is a feed forward system. In a feed forward system, what we are doing, we are not waiting for that disturbance variable to impact on your system. Before that, you start acting. So in this case, you directly measure the disturbance variable Ti, and if this Ti is varying beyond the set point value, in that case what you do? You start applying the control action. So even before that Ti is impacting your system, you have started acting on it, isn't it? So typically in such cases what we do is we measure the Ti by using the thermocouple. Since my control variable here is T instead of Ti, so what we do is we convert this measurement of Pi to T by using some model. So you will see that in feed forward control system you typically require a model, and that model is going to estimate the actual value of the temperature inside the reactor, and that is why this particular Tm is nothing but the estimated value of the temperature inside the reactor and not the actual one. It is estimated. You are estimating this Tm based on the value of Ti. Okay. So when I am saying estimation, what it means is you require a model in terms of a empirical model or database model or some mathematical model you require in order to convert the value to Tm. Okay. We will get more detail on this later on when we will look at feed forward system in much more detail towards the end of this course. Okay. So just to give you a glimpse of what we are trying to say here, that's why this particular figure is here. Is it clear? Then we have argued that this particular system has a theoretical potential of perfect control. It has a theoretical potential of perfect control. Why? Because even before the system is affecting, even before the disturbance is affecting your system, you have started acting, isn't it? So it has a theoretical potential of perfect control. But feed forward system also has one drawback, and that drawback is you have to identify the disturbance. You have to identify whether the disturbance is in Ti or Fi. You have to pinpoint and identify your disturbance, and that's not easy. In this case, it is easy. But in a real plant, when you have thousands of variables, identifying which variable is disturbance is not easy. And that is the reason why, even though feed-forward system is better in terms of control, people still prefer to have a feedback system. Why? Because you don't need to identify the disturbance in feedback. You only need to measure the impact here. Okay. Clear? So this is what we have seen in the last class. In some example, how we can make the inherently unstable process stable, and how we can do online optimizing control. This is what we have seen in the last class, isn't it? One more tutorial for one batch we have done. along the similar line, like optimal control. So there is one more announcement. Tutorial will be held in workshop 101. So in the last tutorial class, there was some problem in accommodating number of students. So we have changed the venue to workshop 101, WS 101. Okay. Alright. So sitting capacity there is 110 students. So we can accommodate reasonable number of students there. Okay. So we will have the tutorial in the regular slot 2 to 3 Monday and 2 to 3 Friday. Correct? But it will be held in workshop 101, not in LS 621. Instead of LS 621, it will be in workshop 101. Okay, so up to this we have seen in the last class. Let's look at some more detail today. So based on whatever the discussion we had so far, we wanted to apply the control for 3 different cases. The first case is whenever there is a change in the disturbance variable and we wanted to suppress the impact of this disturbance variable on the system. Isn't it? That's the first reason. Another reason is to make inherently unstable process stable, and third one is to optimize the process. Correct? These are the 3 requirements for which typically the process control is called. Correct? Now whenever we are saying that we wanted to control a system, what it means? We are trying to put some external intervention in the system so that some of the control variables we will maintain within the given set point value. Isn't it? That is what the control means. Isn't it? But in order to add some external intervention, the important thing required is you need to know the system first. Unless and until you know the system first, you will not be able to make any intervention in the system. Isn't it? And how you can know your system? Either you perform large number of experiments and then you get the feel of the experimental setup of the system, isn't it? That is one way of doing it. Another way is either you model the system in terms of mathematical equation and then you can find out how different variables are changing with respect to time, isn't it? So in the process control, the most important step required is to model the system. Unless and until you know your system, you will not be able to do anything with your system. Any external intervention can be included only and only if you know the system well. Isn't it? So that is what is written here. Okay. So you can see that we require a model primarily because knowing the system is nothing but modeling the system. Isn't it? Correct. So same thing is written here. You can see that how the desired control variables behave in presence of disturbances or changes, or if there is a change in the manipulated variable, how your system is going to respond to these changes. This is required to be known. This is required to be known. Isn't it? Correct? And you can get this information by 2 ways. The first way is experimental approach. In the experimental approach, what you are going to do is you are going to perform large number of experiments. Isn't it? And then based on this experience, you can say clearly that if you change a particular value of the variable, let's say temperature from 500 to let's say 510, what effect is going to have on your output. Something of that sort you have to find out. Isn't it? Correct. The typical way is design of experiment, where you are varying different variables and then you are getting the information about the system. Isn't it? Clearly this particular process is cumbersome. You have to perform large number of experiments by varying the disturbance variables and manipulated variables, and you have to observe how the changes in the manipulated variables and disturbance variables impacting your control variable. Isn't it? Correct. Large number of experiments you have to perform. So clearly this particular process is cumbersome, time consuming, and even sometimes cost is involved, resource consuming. Correct. Now another difficulty is, I don't know whether you know about EPC companies, engineering, procurement and construction companies. With which constructs big plants, isn't it? So you can see that whenever you are constructing a plant, the plant is constructed by including everything, your control system. So in such cases, you don't have choice of doing the experiment. You have to design the control system even before the experimental setup is actually procured. You don't have that choice. You have to design the control system a priori. So in such cases, the only way out in such cases is to model the system in terms of equations and then develop the control system, and that you implement in the plant, and then you do the commissioning. If there is some minute changes are required, that you can implement in the commissioning. That's how the engineering plants or process plants are constructed, isn't it? Correct? So that is the theoretical approach where you are actually representing your system in terms of mathematical equations. Typically these mathematical equations are differential equations and algebraic equations, isn't it? And the differential equations and algebraic equations are solved, and by solving these equations you can find out how your control variables or how your output variables are going to change with respect to time if there is a change in some variable. Isn't it? Is it clear to you what we are saying? Those who have attended the tutorial, they might get some information about this, isn't it? Along the similar line we have discussed in the last tutorial, isn't it? Correct? So the topic here is why model is needed. The precise reason is, in order to know the system, we need to have a model. Model is nothing but what? Model is nothing but the set of mathematical equations comprising differential equations and algebraic equations which you obtain by performing mass balance, energy balance, momentum balance, component balance. These are going to give you the mathematical equations which you have to solve in order to understand how your output variables are going to change, if there is a change in disturbance variable or if there is a change in manipulation change. Is it clear to everyone? Yes, no? कॉन्फिडेंस नजर नहीं आ रहा है, जोर से बोलिए। यस सर। हाँ, अब अच्छा लगा। ठीक है, ओके। So what type of equations we have to solve? Typically, the balance equations we have to solve in order to get the model. And this balance equation is a generalized form of balance equation, isn't it? So accumulation is given as input minus output plus generation minus consumption, isn't it? And you can apply this particular equation on fundamental quantities like mass, energy, momentum, component, and you will get the balance equation in the form of differential equation or algebraic equation. So whenever you are solving a system dynamic condition, system for a dynamic condition, in that case you will get a differential equation, and if you are solving it for a static condition, you will get algebraic equation. So you will get either differential equations or algebraic equations based on whether you are solving it for dynamic conditions or static conditions. So this particular part we will see little bit in more detail. So what we are saying is, in a feed-forward control or inferential control, you require additional mathematical equations in the form of model in order to convert measurement of secondary variable to a primary variable. Remember the same thing we have said here. Here the measurement is Ti, which is a secondary variable, and from Ti we are estimating T. We are estimating T, isn't it? And you require a model. A similar thing is performed in a inferential control. What is inferential control? We will come back to this later. Okay. Okay. Now these are some definitions are given. So in this case, remember I said the state of the system should be known at any time in order to perform the control, isn't it? So in this case, the same thing is written, a set of fundamental dependent quantities whose value will describe the natural state of a given system are referred as state variables, and equation describing how the state variables are changing with respect to time are the state equations. Okay, there are several fundamental quantities of education like mass, energy, momentum, component, isn't it? And we are interested in finding how mass, energy, momentum and component are changing with respect to time. Okay. Everything is there in the book, my friends, but you will not be able to see it. Please pay attention. So I see that most of the time, all this smile and everything may vanish after the smile. People feel that you are open books, you will be able to do it. But my experience tells me that it is far more than that. Alright, so where we are? So there are fundamental quantities like mass, energy, momentum and component. Balances of these we have to see, isn't it? A typical balance equation is given on a quantity S. So you can see that the accumulation of S within the system with respect to time, flow of S in the system, flow of S out of the system, and plus generation of the S in the system and minus accumulation of S in the system. This is the same equation which we have written in the form of fundamental quantity S, where S can be total mass, mass of individual component, total energy and momentum. So this particular balance equation will give you algebraic equation or differential equation depending on whether you are looking at a static condition or a dynamic. Okay. We will start with one example, then you will appreciate what I am trying to say here. So let's start with a simple balance equations here. So if you look at the mass balance, typically the mass balance is given as how the mass inside the system is changing with respect to time. So you can represent that as volume into density, isn't it? So volume into density, that will give you mass. So d rho v by dt, that is giving you how the mass is changing within the system with respect to time, isn't it? And that is given as summation of rho I fi. So whatever the material coming in the system minus summation of rho j fj. So whatever the material going out from the system. Okay. In this case rho I and rho j, these are nothing but the density of the input and out, and fi and fj are the flow rate, volumetric flow rate of material coming in and going out. Correct? Alright. Similarly, the component balance, this you might have studied in reaction engineering. So component balance is how the moles of a particular component changing with respect to time. How I can get that? dNA by dt. So Na is the number of moles of A. So dNA by dt is nothing but the change in moles of A with respect to time, and that can be given as d by dt of CAV. So Ca is the concentration, V is the volume of the reactor. Isn't it? So d by dt of CAV, that is given as CAI Fi minus CAJ Fj. So CAI Fi is nothing but the inlet, CAJ Fj is the outlet, and in addition to that we will have reaction occurring inside. So because of that there will be consumption, or we can have even the production of A, isn't it? So that is represented as RAV. Plus or minus is given based on whether the A is getting produced or whether A is getting consumed in the reaction. Okay. Third equation is the energy balance equation. So how the energy is changing inside the system. So here the energy, if you are looking at, there are three types of energy, isn't it? Internal energy, kinetic energy and potential energy, isn't it? So you can see that whenever we are looking at the process systems where everything is within the reactor, hardly the kinetic energy is changing, hardly the potential energy is changing, only the internal energy is changing. So we can write this equation, we can simplify this equation as du by dt, and that will be equals to summation of whatever the energy coming in. So here you can see that Hi is the enthalpy multiplied by flow rate multiplied by rho I. So this gives you a mass flow rate multiplied by Hi. So this enthalpy is per unit mass, per unit mass. This term is the outlet, is the inlet, is the outlet, and in addition to that the energy is taken out or sometimes supplied to the system. So that is accounted through Q. If the energy is taken out in that case, the Q will be negative. If the energy is supplied to the system, in that case Q will be positive. And in addition to that, there will be one more term which is work done. Work done. Okay. So this is the energy balance equation. And in addition to that, there is one more balance equation which we hardly use in the process control, but you might have studied in transport phenomena. Isn't it? So this equation is a momentum balance, how the momentum is changing with respect to time. So here, how the momentum is changing with respect to time is nothing but the force balance. Inlet forces minus outlet forces, that is what we are doing. And if you simplify this particular equation, you typically get a Navier-Stokes equation. Okay. But you will see that in this particular course, we are not going to look at this particular equation at all. This equation is not new. Because whenever we have a reactor system, we are not taking that material every time out, isn't it? So flow is not important. So you will see that only these three equations are predominantly used when we look at the process control. Okay? Is it clear to everyone? Yes, no?
Yes, sir.
So let's start with our usual simple, toy problem of stir tank heater. Get it? So in this stir tank heater example, you can see that this is the stir tank reactor. In this case, you can see that the component A is coming in with the concentration of CAI. Isn't it? Fi is the flow rate. Isn't it? Ti is the temperature of the inlet feed. Outlet from this reactor is Ca, F and T. Ca is the concentration of A coming out from the effluent, F is the flow rate and T is the temperature. Correct? In this particular stir tank reactor, there is a reaction occurring which is A gives R and this particular reaction is exothermic. Your friends are also interested in that topic. Okay. So in this particular, so see, people don't like because that kind of disturbs my disturbs my disturbs the environment. If you are not interested, stay. Don't come. I will mark your attendance. Stay. You are not interested. I am okay with that. Alright. So there is a exothermic reaction occurring. So heat is liberated and that heat has to be taken out by the coolant which is flowing through the jacket. So here you can see that the coolant flow rate is Fc and the temperature of the coolant is Tci, which is the inlet temperature, and the outlet temperature is Tc0. Coolant flow rate we are keeping it constant, so only the temperature is changing Tci to Tc. Okay. Now if I wanted to model this particular system, So first look at the mass balance in this case, isn't it? So mass balance in this case, whatever the mass coming in, isn't it? Whatever the mass going out, isn't it? And based on that, you wanted to find out how the mass is going to change within the system, isn't it? So the total amount of mass present here inside this particular tank will be given by what? How it is going to change with respect to time will be given by what? d by dt of rho v. So rho is the density of the liquid, v is the volume of this reactor or reaction mass, and d rho v by dt is going to give you how the mass inside the system is going to change with respect to time. Correct? And that will be given by what? The material coming in minus material going out, so rho Fi minus rho. Isn't it? If you assume that the density remains constant, in that case we can take this density out from this equation and we will get dV by dt is given as Fi minus F. Isn't it? One more simplification we can add here. So volume of the liquid present inside the tank is given by what? Cross sectional area of the tank multiplied by the height of the liquid present in the tank. Isn't it? So if you take the height of the liquid here as h, in that case A into h is the volume. So we can simplify this equation further as A dH by dt is given as Fi minus F. Okay. So this particular equation is the mass balance when we are looking at a state and reactor system, and we are going to use this equation directly later. Okay. Don't expect that we will derive these equations again and again. Okay. Some of these simple equations we are going to write directly later. So the mass balance in this case will be given by A dH by dt, which is Fi minus F. Now let's look at the component balance. So component balance is given by dNA by dt, isn't it? Which is nothing but d by dt CAV, correct? d by dt CAV, and this component balance will be given by what? Whatever is coming in, whatever is going out, plus whether A is getting produced or whether A is getting accommodated using the rate of reaction, isn't it? So in this case A is getting consumed to produce R. So our equation will be CIFI, isn't it? So that is the number of moles with respect to time coming in the system. CAF is nothing but the number of moles of A going out from the system, isn't it? And the A is getting consumed inside the reaction, so that will be accommodated through minus RAV. So minus RAV means the A is getting consumed, correct? So this is the equation. Now we can simplify. So this dCAV by dt is there. We can expand this particular term. So if I expand this particular term, what I am going to get? Ca dV by dt plus V dCA by dt. We are only interested in dCA by dt. So in this case, this Ca dV by dt is there. So this dV by dt we have already calculated. See, dV by dt is Fi minus F. So we can put that in this equation. If we put that and simplify the entire thing, what we get is V dCA by dt is given as Fi into Ci minus Ca minus RAP, isn't it? And then Ra is expanded here. So if you are assuming that this is the first order reaction, in that case the Ra will be given by Kca or K naught e raised to the power minus E by RT into Ca, isn't it? So the same thing is written here. So later on you will see that whenever we will look at the state tank reactor system, we will write the component balance directly. So this component balance is nothing but what? Whatever the inlet flow rate is there, Fi into Cai minus Ca. Cai minus Ca. So there is some generalization is there. In fact, the same generalization is applicable when we look at even the temperature equation. And we are going to write this equation directly without deriving again and again. Okay. So the equation here is V dCA by dt is given as Fi Ci minus Ca minus V K naught e raised to the power minus E by RT to Ca. Now let's look at the energy balance. So in the energy balance, as I said, there are three types of energy, isn't it? Internal energy, kinetic energy, and potential energy. If you look at this reactor system, will the potential energy going to change? I am not changing the height of the liquid, and this remains same. Potential energy will remain the same. Kinetic energy, because of stirring, there could be some change in the kinetic energy, but usually we neglect that compared to the energy change because of temperature. So the only term which is useful in this particular case is internal energy. So internal energy will be represented by what? mCp/dt. mCp/dt is the internal energy. So m mass you can obtain as rho into V is mass into Cp into delta T. Isn't it? So T minus T reference temperature is taken here. Isn't it? And this entire equation will become d by dt of rho v Cp T minus T rate. So that is nothing but the change in the internal energy. Now change in the internal energy will be given by the amount of energy coming in the system, isn't it? So that we can obtain as the enthalpy of the inlet feed multiplied by rho FICP, isn't it? So this is the amount of energy coming in with respect to time in the system. This is the amount of energy going out from the system. You can note down that here the delta T is Ti minus T ray. Here the delta T is T minus T ray. Okay, that is what you have to note down. And the last term here is because of reaction. Remember, in this case we are saying that the reaction is exothermic. So heat is liberated. So the amount of heat liberated will be given by heat of reaction multiplied by RAV, isn't it? Minus the amount of heat taken by the coolant, which is given by Q. Okay. So this is the equation which we have obtained here. Now T rate reference temperature can be any reference temperature. It should be valid for all the reference temperatures. I can take even T rate as 0, isn't it? Doesn't matter. Correct. So same thing we have done. So we can take the T reference equals to 0. In that case we can get dVT by dt is FITI minus FT plus minus delta HR RAV divided by rho Cp minus Q by rho Cp. So we have taken this rho Cp and we have divided this entire equation by rho Cp. Correct? So now again in this particular case you can see that you are getting a left hand side which is d by dt of Vt. We can expand this particular term, so that becomes T dV by dt and V dt by dt, isn't it? So that is what we have written, V dt by dt plus T dV by dt, and dV by dt we already know that dV by dt we have already taken as Fi minus F. So we can put that again back to the same equation. And further if we simplify, what we get is V dt by dt is obtained as Fi Ti minus T. So you can see that there is a generalization here. Inlet flow rate into inlet temperature minus outlet temperature. Isn't it? Same generalization we have used here also. See, inlet flow rate into inlet concentration minus outlet concentration. Okay. And the other two terms are, this is the term because of the heat of reaction, and this last term is because of the amount of heat taken out by the coolant. Isn't it? Further we can simplify this Q. So Q is nothing but what? The amount of heat taken out by the coolant, and we can write down this equation in terms of Newton's law of cooling. Isn't it? This is known as HA delta T, correct? Or UA delta T. U is the overall heat transfer coefficient, A is the heat transfer area, this AT is the heat transfer area, and T minus Tc, where Tc is the coolant temperature. Okay. And we can simplify this particular equation like this. So this is the final equation we are getting. So you can see that for the given system now we have three equations. These three equations are how the volume is changing, dV by dt. Then we have another equation, how the concentration is changing, dCA by dt. And the third equation was how the temperature is changing, dT by dt. So these are the three variables which are defining the natural state of the system. Natural state of the system. So that is what is written here. You can see. So here H, T and Ca. So these are the variables we are monitoring. Isn't it? Our control objective is to what? Our control objective is to maintain the height of the liquid in the tank and also to maintain the temperature inside the tank. So those are the control variable, and in order to maintain this, the manipulated variable in this case are, the manipulated variable is, we can manipulate the outlet flow rate, we can manipulate the temperature here, we can manipulate the coolant flow rate here. Clear? Is it clear? How the system is modeled? So this is one simple system I have modeled, but in the book there are several examples are given. I am not doing that. That you have to do yourself. Okay, there are I think 3-4 modeling systems are there. If you are having instead of single input, let's say if you are having multiple input, how your equation is going to modify. This is the Stir tank reactor is there, but let's say instead of stir tank reactor, if you are having, let's say, plug flow reactor, how the modeling equations are going to change? Here you are taking a reactor, but let's say instead of reactor, if you are having a heat exchanger, what type of equations you are expected to get? All those systems are solved in your book. Please look at the model equations for the different systems which are there. I will not be able to cover each and everything, whatever is there. Okay? Is it clear to everyone? So state variables here are H, Ca and T, and constant parameters are rho, A, Cp and reference temperature. So in addition to these model equations, some more equations you require when you are solving the system. Okay. So whenever you are solving the model equation, you need to make sure that the thermodynamics is also in sync with what you are doing. Isn't it? For example, let's say the vapor and the liquid present in the tank are in the equilibrium. So whenever I am saying that vapor and the liquid, those are present in the tank are in equilibrium, what it means? It means that the temperature of the liquid and the temperature of the vapor should be same. Pressure of the liquid and the pressure of the vapor should be same. And in addition to that, the chemical potential of the liquid and the chemical potential of the vapor should be same. Then and then we can say that vapor and liquid are in equilibrium. Another requirement is very often you need to satisfy the equation of state. A typical equation of state used is PV equals to nRT, isn't it? That is for ideal gas. You can use the another equation of state like Van der Waals equation, isn't it? Instead of using this equation directly, very often you find out the density of the mixture as Pm by RT. Whenever you are having a mixture, what will be the density? That will be given by Pm by RT. So these are the equations usually we overlook and we end up with get solving the wrong system. Why I am saying wrong system? Typically, if you miss the degree of freedom here, you are going to get a wrong answer. Isn't it? So when we solve the distillation column, typically we have 25 to 30 equations are there. If you miss even one equation of state, you are going to get beyond the state. So all these equations coming from kinetics as well as from the thermodynamics has to be satisfied. These are the kinetic equations given here. How the heat will be transferred from coolant to the reactor, that is given by this equation, which is UA delta T, isn't it? And this is the equation for how the rate of reaction will vary. So that is given as K naught e raised to the power minus E by RT by Ca, where K naught is the Arrhenius quantity. Correct? Now coming back to another important concept. Okay. So whenever we are applying any intervention in the system, do you think that this intervention is going to impact the system immediately? It's not going to impact immediately. It's going to take some time. For instance, you might have done this example in reaction engineering, isn't it? Whenever you are adding a pressure in a flow reactor, the impact of that pressure will be felt in the outlet after some time. After some time. It's not going to happen immediately. Correct? So there is always a dead time or a lag time associated with the system. And you will see later that this particular dead time is the most detrimental factor in the process control. In fact, this is the most detrimental factor. Typically, the systems those are stable becomes unstable even if there is a very small dead time, and we will prove as we will go ahead. Okay. In fact, there are the control systems which are developed in order to handle the dead time separately. That also we will see towards the end. Systems with large dead time. Okay. Example given here is, let's say if you are having a plug flow reactor, I can find out how much dead time which is there associated with the given plug flow reactor. How I can find out? Volume of the pipe divided by volumetric flow rate. I will get the typical value of dead time. Okay, so volume will be given as area into the length, isn't it? Divided by volumetric flow rate, that is nothing but A into V, average velocity. Here V is nothing but what? Average velocity. You will get a delta in T. So you can see that your output is dependent on input, but then the input will be function of T minus Td, and this entire function we call it as a translated function. We will understand this particular equation little bit more when we will look at Laplace transform. Okay. So these functions are called as translated functions. So what it means is, whenever something is changing in the input, the output will be impacted after Td time. It's not going to happen immediately. And you can simplify this equation mathematically. You will get e raised to the power minus Tds term if you take a Laplace transform here. Okay. Is it clear? So I am not covering this part in detail right now, but as we progress, you will understand this term a little bit more. Okay. When we will look at the Laplace transform. Is it clear to everyone? Okay. So far everything was very good, isn't it? We started with a system. Initially we started with why process control is required. Then we argued that for the process control, knowing the system is very important. So for that, then again we said that knowing the system is nothing but knowing the model of the system, isn't it? Then we said that in addition to the usual modeling equations, you also require the equations from thermodynamics, you require the equations from kinetics, isn't it? That is what we said, isn't it? There are some difficulties in this. There are some difficulties. Okay. What are the difficulties? First is, we have assumed that K naught, activation energy E, or the overall heat transfer coefficient U, we have assumed them as constant values, isn't it? But do we know their values accurately? How these values are found out? These values are found out by performing the experiments, isn't it? And there is always the error associated with whatever the experiments you do. If there is a change in these variables, how these changes are going to impact your actual process control, that we have to see, isn't it? Okay. So whenever such variables are changing, there is something called as adaptive control. Towards the end, we will see even that topic. How adaptive control can be used, where the parameters can change dynamically in the system, and you are adapting based on the change, and you are performing the corrective action. Okay. So adaptive control also we are going to look at towards the end. Then we have assumed that Cp and rho are the weak function of temperature. But how weak? During the operation, so if you are performing the reaction in a reactor, you will see that the catalyst which you are using will be degrading day by day. Correct? So you have to regenerate your catalyst. If you are using a heat exchanger gets fault, isn't it, over the time? So your system is non-stationary. Such systems are called as non-stationary. That means whatever the experimental setup you are using today will not be same as whatever the experimental setup we have used yesterday. Your system is changing over the period. It's a non-stationary system. Okay. The order of the reaction must be correct. Sometimes the process is poorly understood, and very often we wanted to increase the accuracy, but in order to increase the accuracy, typically your system becomes more and more complicated. It becomes so complicated that you are not able to solve it. Isn't it? So you have to make that balance between accuracy and the complexity of your system. Isn't it? I can model the system accurately, but then if I am not able to solve it, what will I do? Remember the Navier-Stokes equation is the accurate form of the energy balance. So you are not able to solve it. You have to do some assumptions and then solve. Right? So you have to make the balance between the accuracy and the complexity. So before we stop today, I will just give you a brief about different types of variables those are present in the process control. Okay, we started with why process control required, then we looked at why the model is required, and now we are going a little bit in detail in how the process control will be implemented. So when we are implementing the process control, the first question comes into the picture is what are the different variables present in the system, isn't it? So if you look at the variables present in the system, there are two types of variables, input variables and output variables, isn't it? Input variables, some variables are those variables which you can change yourself, isn't it? Like flow rate, etc. You can change yourself. So all those variables are manipulated. The variables which you can change at your own discretion, these variables are referred as manipulated. And the variables, those are not, you will not be able to change them. These are coming from the previous equipment. All those variables are disturbances. Then output variables. If you look at the output variables, some of the output variables you can measure. So all those variables are called as measured output variables. And some of the output variables you cannot measure, but you require their values to be known. In such cases, what you do? You measure some secondary variables and then use that model, use some model in order to convert the secondary measurement to the variables of your input. A typical example is, I don't know whether you have visited any oil industry or not, but if you look at the distillation column there, so distillation column control, if you look at, they don't measure the concentration. Remember, their objective is to maintain the concentration of product coming out from the distillate and the concentration of the product coming out from the bottom. But if you measure the concentration, concentration is measured by what? Concentration is measured by HPLC. It is going to take 1 hour. So it is not feasible. By the time you get the value, everything is measured up in your system. So you don't measure the concentration. Instead of that, you measure the temperature of different grades. And temperature of the different grades, you convert it into the concentration. So you measure the secondary variable and then you use the model to estimate the primary variable. That is what I am saying. Sometimes the variables are unmeasured and you can find out the values of these unmeasured variables. You can estimate the values of these unmeasured variables by using the model. Okay. So this is the schematic representation where this is the process. There are external disturbances which are measured, unmeasured. There are unmeasured output, there are measured output, and there are manipulated variables which you are giving as an input to the system. Okay. So we stop here and we will continue from this point. Okay. All right. If you have any problem, you know, concentrating here because I am mostly stand there. Start block. You can
let us not create problems for